Full introduction, Connor. I'm going to bring my slides up real quick. Here we go. That's not what I wanted, sorry. There we go. All right, thank you so much, Connor, for that introduction. My name is Emily Whitcup. I use they, them pronouns. Today I'll be presenting on the solvation properties of selected persistent organic pollutants and the relationship to the bioconcentration factor. First of all, what are persistent organic pollutants? Persistent organic pollutants are compounds that persist, bioaccumulate, and pose significant health risks to flora, fauna, and of course, humans. Many pesticides are persistent organic pollutants, and many persistent organic pollutants are pesticides. And from here on out, I am going to say POPs, because otherwise it's a bit of a mouthful. The Stockholm Convention, which is a subset of the United Nations, identified 12 compounds in 2004 that started off this list of POPs, and they have been identifying more since then. Currently, there are 35 compounds or families of compounds. I do say families of compounds because they generally just list either a single compound that can have a lot of degradation products or photochemical products that are quite bad for the environment as well. Or sometimes they are a class of compounds that can, including one that contains over 200 distinct compounds. The most well-known POP is DDT, which is listed over here or shown on the right here. It was identified in 1962 in the book Silent Spring by Rachel Carson, where she went through a lot of data that, including some data about eagle eggs that showed that DDT was really harmful for the environment. Specifically, DDT was identified using eagle eggs because they showed some of the early signs of really harmful effects on the environment. And the reason this title says selected POPs is because for the computational study, we selected a set of POPs that are compatible with computational methods. Most of them have very rigid ring structures, which makes them more compatible for computational methods, which I'll discuss a little more later. The 4 families of compounds that we chose were Aldrin, Chlordane, Endosulfan, and Hexabromocyclododecane, or HBCDD. So first of all, here are Aldrin and the related compounds that we used in this work. I want to highlight a few things. First of all, Aldrin and isodrin are stereoisomers. You can see right here and right here that they have that bridge there, and one of which goes forward and the other goes backwards, that the dashed lines being the ones that go back and the wedged ones being the ones that go forward. Then we have dieldrin and endrin, again showing that same stereoisomer relationship on the same spot, but these both have an epoxy group. And then we have a couple photo products, photoaldrin, photodieldrin, and endrin ketone. First of all, a little bit about aldrin and photoaldrin. The difference here being that this double bond is not here on this side, but a new bond is formed along the back to the top of this bridge. I want to note that I have specifically drawn them like this, especially photoaldrin. This is a bit of a weird drawing to look at, but I put that in there so you could really see where that connection is. The real compound is really boxy and kind of folds back on in itself. It's really sterically unfavorable. Here we have dieldrin and photodieldrin, and you can see that the same connection is made between these two photo products. And then endrin and endrin ketone. This one is a little different because rather than forming to the top of this bridge, it goes around back and forms this ketone product. All 3 of these are really boxy photochemical compounds, but I've just drawn them like this for ease. Here are Chlordane and the related compounds. First of all, there is cis and trans Chlordane. Cis Chlordane on the cis conformer here on the 5-membered ring, and the trans conformer over here on the 5-membered ring. Here is oxychlordane. I'm sorry that this keeps popping up. I'm going to stop moving my mouse for a second, where you can see the epoxy ring that is formed on the 5-membered ring. And then over to the right, on the top, there's heptachlor. That heptachlor has that double bond in the 5-membered ring and only one chlorine. Heptachlor degrades into both heptachlor epoxide with the epoxy ring and photoheptachlor. I want to note photoheptachlor in this one is a little different because you have 2 double bonds on either side. So both double bonds break and form bonds across the back of the compound. Again, it's kind of boxy and it folds back on in itself, and it's again sterically hindered. Here is endosulfan and the related compounds. I want to note that this is the degradation pattern in water. The degradation pattern in soil is a little different, but uses the same compounds. So first off, there's alpha and beta endosulfan over here. The difference is right here where we start that 7-membered ring. Alpha endosulfan is a bit of, if you look at it from the side, is kind of zigzagged, whereas beta endosulfan is like a big loop because of the way it bends in on itself. I do also want to note that the only reason I have used the dashed lines across all of these is because I was following the same path from beta endosulfan. It could just as easily be switched to the alpha endosulfan pattern and have a wedge here instead of a dash. I just wanted to keep it consistent throughout. So beta endosulfan degrades into endosulfan sulfate, which is the very first one at the bottom left, where you get an extra oxygen double bond on the sulfur. Both endosulfan sulfate and the base endosulfan can degrade into endosulfan diol, where you get 2 alcohol groups right here. Endosulfan diol degrades into endosulfan ether, creating the ether group on the end here. Endosulfan diol can also degrade to hydroxy ether, giving you the ether and your hydroxy group. And the endosulfan hydroxy ether can degrade into endosulfan lactone, where you have your ether and the ketone making a lactone group. And lastly, HBCDD. Hexabromo because there are 6 bromines, and cyclo because it's a ring, and dodecane because there are 12 carbons. You'll note that this one looks pretty different from all the other ones. We wanted to test out a compound that was not sterically hindered to see how it reacted to the methods we used. There's alpha, beta, and gamma. The differences being just these back and forths on the bromines. So I want to talk a little more about photochemistry and degradation. I've used those words a lot in the last few minutes, and I want to kind of clarify that. A lot of the compounds I just talked about were used as pesticides, insecticides, so on and so forth. So a lot of times they were sprayed onto crops. Because they were sprayed, they ended up dispersing into the atmosphere really easily, which encourages photochemistry. This photochemistry is encouraged because there are more UV rays, there's less protection against the UV rays as you get higher in the atmosphere, and there's more ozone, so there's more oxygen available for reactions. Compounds, of course, can also degrade other ways in the environment, mostly through soil and water. Again, 2 things that are really easy for these chemicals to come into contact with when they're used as pesticides. The soil has different reactions that can happen because of all the nutrients in there for plants. And water, of course, has different reactions that a lot of them have to do with acid-base chemistry. And I want to talk a little more about stereochemistry. Stereochemistry is a lot easier to define in computational methods and to study specifically because you can define it in your input rather than having to do extra tests on a physical compound or a physical solution. And stereochemistry is massively important. I want to bring up thalidomide, which a lot of us probably heard about in OChem, but I just want to kind of bring it back up. One stereoisomer of thalidomide was a morning sickness medication in, I believe, the 70s, but they found out after not very long that the other stereoisomer of thalidomide caused pretty bad birth defects in the children of mothers who used it as a morning sickness medication. So stereochemistry can lead to some pretty grisly effects when it's used in medicine, and it can have different effects on how things work as we move forward in this study. So a couple important terms and ideas outside of the ones I just talked about. First of all, the bioconcentration factor. The bioconcentration factor is the ratio of the concentration of a compound in the tissues of a living thing to the exposure concentration, specifically inhalation exposure. A lot of times it's studied in fish, so it's the concentration just in the water that the fish live in. This bioconcentration factor changes depending on the species, and it can give information about environmental movement because of bioaccumulation and biomagnification. So the way that these compounds could move through like the food chain as they bioaccumulate going up the food chain, which is why we saw the effects of DDT in eagles before anything else. Next is the octanol-water partition coefficient. The octanol-water partition coefficient compares solubility in octanol in water. Octanol is used because it simulates organic environments while still being a well-known substance and not having a ton of weird things happening in it that you sometimes see with other organic solvents. The octanol-water partition coefficient is denoted as the KOW, K being the coefficient, and then OW, octanol water, and it's often reported as the log of the KOW. You can also use olive oil instead of octanol, in which case it's denoted as the KVOW, and the olive oil can be used to get a more accurate representation of an organic system and organic fats. At the very bottom of this slide here, I have the equation for the KOW. The log KOW is equal to the negative Gibbs free energy of solvation in N-octanol minus the Gibbs free energy of solvation in water over the gas constant times temperature times natural log of 10. The temperature used throughout this study was room temperature, 25 degrees Celsius, 298.15 Kelvin. And then what is the relationship between BCF and KOW? Correlation of bioconcentration factors was a paper published in 1982 by Donald McKay. This paper compared known BCF values and known KOW values of about 50 compounds. And this paper also provides a few equations to calculate the KOW from solubility and melting point of a compound. And McKay's paper found a linear relationship between the bioconcentration factor and the KOW. This was super valuable at the time. This was the 80s, so computational methods were not very sophisticated yet. And it was a really great way to find KOW and BCF from information that was easy to study in a lab. Lastly here, we have the purpose of this work. The purpose of this work was to investigate this relationship between BCF and KOW, especially testing computational methods that are available to us now in 2021, though it's done in 2020, and to use this relationship that we potentially could find to learn more about less studied compounds, such as our photochemical products and our other degradation products. So I'd like to take a quick break here and get some questions about some of the compounds and terms I've talked about so far. I'd like to take 2 or 3 questions now. Sorry.
As a reminder from Alyssa, if you have a question, please find the participants panel or the reactions button and raise your hand. Saffron?
Yeah, a couple slides back, you mentioned something about octanol not allowing weird stuff to happen within the water. What does that weird stuff exactly mean?
Yeah, I should probably specify. So, and I think maybe I made this unclear. So compare the KOW does not take like the solubility of octanol in water, but it compares 2 separate solubilities between octanol, so the compound in octanol and the compound in water. Part of why I said no weird stuff with octanol, especially compared to olive oil, is that like octanol is a compound that's just one long chain with the OH at the end, whereas olive oil has a lot of different stuff going on in it. So really why we use the octanol is because it makes the computation is a little faster for octanol than it is for olive oil, and it still simulates an organic environment well enough. Does that answer your question?
Yes, thank you.
Awesome.
Elijah.
Hi, I was wondering why there's a relationship between that bioconcentration factor and the KOW?
Yeah, for sure. So the reason there's a relationship between bioconcentration factor and KOW is because a lot of the compounds that we study are stored in fat cells. And much to the chagrin of a lot of American women, fat cells are stored for a long time in the body. Fats and comparatively, our water-based bodily liquids are not. And so things will store really well in these fatty cells, which are approximated by both octanol and olive oil. Whereas things that are, so if things dissolve really well in octanol or dissolve really well in olive oil, they're going to be stored in the fat cells in your body, and therefore they are going to store in your body longer than anything that would dissolve in water. Joe, did you have a question? Because I saw your hand was raised and now it's not.
I was just wondering if you could clarify organic environment versus biological environment.
Yeah, so when I'm saying organic environment, I'm talking more about like organic compounds like octanol or and whereas a biological environment can contain and does contain a lot of both organic and inorganic environments, and really inorganic in this case really just means water. So biologic and organic are not the same in this case, which is definitely worth noting and remembering going through this. So there are in the body, there are both organic and inorganic systems. It's just about what compounds those are primarily made of. And when I'm talking about an organic system in this case, I'm usually talking about what our octanol and olive oil solvations will estimate.
Okay, thanks.
Okay, barring any other questions, I'm going to move on. So now I want to talk a little bit about the methods that were used here. So first of all, ALOG PS 2.1. ALOG PS 2.1 is a free online program that calculates both solubility and KOW of a compound just by inputting what's something called a SMILES code. This here is the SMILES code of Aldrin. I certainly don't know how to write something in SMILES code, but SMILES codes are available on PubChem for most compounds. So you can just copy and paste it out of PubChem, which is really useful. And so here I have the readout for ALOG PS 2.1. This first value here, 5.90, is log P, which is the same as the log KOW. The second one here is the log of the solubility, and then the SMILES code comes back out. The nice thing about ALOG PS 2.1 is it's instant. It calculates it super quick. The longest part was waiting for a new browser to load, or a new page to load on my browser. The issue with ALOG PS 2.1, however, is that it does not account for stereochemistry, which of course is something that we looked at a lot in this study comparing stereoisomers. We used ALOG PS 2.1, however, because it's a great way to get an early estimate. It's really fast. It's really easy to use. So it was good to see, especially if we were even getting anywhere and if there was any evidence to say that there was a log KOW and BCF relationship that we were getting from our study with these compounds. The next thing we used was the equations given in Donald McKay's 1982 paper. He provided two useful equations, one for solids and one for liquids. I've listed them down here. So this one here only uses solubility, which is why you use it for liquids. And this one uses solubility and melting point, which is why it is for solids. I want to note again that for temperature, that was like our melting temperature over temperature. Temperature was again room temperature. And here I've calculated that out for Aldrin. Our log KOW calculated from McKay's equations is 5.78, which is really, it's worth noting that's 0.12 away from what was calculated by A log PS 2.1. The issue with McKay's equations, however, is they're only as accurate as solubility and melting point data. If you can't find reliable data for the solubility and melting point for a compound, you're not going to get anything out of this equation. You can't use it at all, which is really unfortunate. And then we used Gaussian. I'm going to talk a little bit about Gaussian before I talk about specifically what we did with Gaussian. Gaussian is a computational chemistry program that's used worldwide, and it's really reliable. We used density functional theory, which uses electron density and functionals for calculations. Functionals are functions of a function, essentially. And for our solvent model, we used a solvent model based on density, SMD, which looks at the solvent and solute relationships and interactions using solvent cavities. I'm going to talk a little bit more about this. So here's just an image that kind of displays a solvent cavity for a generic compound. You can see that there are these bubbles around each atom. Those bubbles represent more or less the electron cloud of an individual atom. And as you put together a compound and combine these atoms, the bubbles around each of the atoms will combine to form this shape, which is then used by Gaussian as our solvent cavity. SMD is different from some other models because it treats the solvent, so either water, octanol, or olive oil, as a homogeneous medium rather than a bunch of individual molecules. So it calculates interactions between our homogeneous medium and this bubble, this solvent cavity, rather than directly against each individual atom. And so for this specifically, we used Gaussian optimization and energy jobs. So this is a DDT input file on Gaussian. So you draw a structure to submit for calculations. It's really important that this structure is pretty accurate from the get-go, but you can use an optimization job type to try and get it to the lowest or the least energetically unfavored. So the most energetically favored version of what you have put in. It's still really important to start off with an accurate structure, because sometimes it won't quite catch what you want your structure to look like, and it'll turn to something completely different after the optimization. After doing the optimization, we did the energy calculation, which finds that Gibbs free energy of solvation using the DFT and SMD methods. So we did 3 separate calculations for the solvation energy, one for olive oil, one for octanol, and one for water. One of the downsides to Gaussian is that it's really time consuming. A lot of the selected POPs took like 20 minutes to run each one for the energy method or the energy job type. And lastly, I do have listed at the bottom the method we used, which was DFT B3LYP/631GD, which is a hybrid functional in density functional theory. So what we found all of these KOW values, but we do need to compare those to known bioconcentration factor values. We used a couple of different sources, but primarily we used the Arno-Gobas database and National Institute of Technology and Evaluation database. That NITE database comes out of the Science and Industry department in Japan, and the Arno-Gobas database is from an individual's company here in the US. And then we had to add data points for other compounds other than the ones that we have selected as our selected POPs. The reason we need to add data points is because a lot of our POPs had really high log KOWs, well, comparatively high log KOWs and comparatively high log BCFs. So we needed more things on the low end of that spectrum. So what we did is we used some of the other compounds that were used by McKay in his paper. A lot of the compounds had a lot of really well-known data, and they gave us some of that data on the low end. Simple structures, well-studied, really fast to run through Gaussian. So things like benzene or chloroform, chlorobenzene. We also used like DDT and a couple other POPs to make sure we had relationships that were fitting more than just the type of structure that we selected. So what were the results of this work? So I have a couple graphs here. Here is ALOG PS 2.1 calculated KOWs compared to the bioconcentration factor. I want to highlight, first of all, R squared value of 0.941. The ideal R squared value is 1. So this is pretty good. But there were 8 points that were removed as outliers using a method of pulling out residuals. But I want to highlight again, despite the fact that this one has a good R squared value, ALOG PS 2.1 does not account for stereochemistry. So we know that this is not perfect. Here we have the log KOW calculated with McKay's equations compared to the log BCF. R squared of 0.906, so a little lower, but still not bad. And 5 points were removed as outliers for this one. Here is the log KOW calculated by Gaussian. We have an R squared of 0.7, which is the lowest of all 4 of the methods I will show, but no points were removed in this one using residuals. So you'll note like this up here, it seems extraneous, but using the method we used to remove outliers, it was not. And then lastly, the Kvow, so a reminder, the octanol, or rather olive oil water partition coefficient compared to BCF using Gaussian. 10 points were removed as outliers for this one. And the R squared value is 0.826. I want to note that this one has one value of the Kvow below 0, which is interesting, and it's the only one that has that. And a lot of the lower data points were removed here. I'm going to go through our selected POPs real quick, just to kind of highlight some of those things that we've noticed. Aldrin and isodrin, 2 stereoisomers, have the same log KOW according to ALOG PS 2.1, but not according to any of the others. And then we also see that same thing in dieldrin and endrin. And then we also see that we're missing a couple values here using McKay's equations because there was no solubility or melting point data. And this is something consistent across all of the different selected compounds. Our Kvow is lower than the KOW when we calculated that in Gaussian. Here are the values for the Chlordane family, and I want to note that the values themselves are not what we're looking at right now, just some of the patterns that we see. We see the same value for stereoisomers. We see a lower Kvow, so the olive oil water partition coefficient, and we're missing one for the McKay calculations. Here's Endosulfan. We did not have much data at all on these compounds, so it was impossible to calculate the KOW using McKay's equations here. And lastly, HBCDD, Hexabromocyclododecane. All 4 of these, of course, gave us the same ALOG PS 2.1 KOW, log KOW, because they're all stereoisomers, but we're not seeing that across any of the other ones. So a quick comparison of the methods used. Like I've said, a lot of times now, ALOG PS 2.1 does not account for stereochemistry, which is really too bad because it's such a simple and easy thing to use. McKay's equations require accurate solubility and melting point data, which is particularly hard to find for our photochemistry and degradation products. I want to note that cited here at the bottom was my primary source for solubility and melting point data. I want to note that's primary as in most used, not primary versus secondary sources, which is the Handbook of Aqueous Solubility, 2nd edition. And Gaussian requires very accurate structure inputs. We can use an optimization calculation, even a semi-empirical one, which is the fastest, but it won't. It's not necessarily perfect to use when you use that optimization. Over here on the right, I've also listed the average deviation of the log KOW between each method, not including the KVOW, because that is a different value that we're calculating. So just between A log PS 2.1, the McKay calculations, and the Gaussian calculated KOW. The average deviation, the mean, is 0.32. The range is 1.15 and the median is 0.24. When I first pulled these up, I thought that wasn't too bad, but when you consider that the total range of KOWs that we found was between 0 and 6.5, that's pretty large. Those are pretty large numbers. So what is the relationship between BCF and KOW according to this study? We can't yet state a definite relationship between the BCF and KOW. We don't have a y equals mx plus b equation. We do know, however, that there is a linear relationship. We also know and have confirmed that stereoisomers have different KOW values, which is particularly interesting because some of the sources that we looked at while looking for data about these compounds listed the same KOW for some of these stereoisomers. And we can say pretty certainly now that that is not true. And what is some of the continuing work? One of the first things would be checking and revising those Gaussian input structures to make sure we're getting the most accurate data out of the calculations. It might also be worth investigating and comparing the different families of compounds to see if we see different relationships for these different families. And I particularly am interested in the photochemical degradation process and kind of looking more into how that works in our atmosphere. Here are a few of my works cited that weren't listed on other slides. Thank you for coming to my seminar. I was so excited to see all the people that showed up to support me. I want to thank my advisors, Alyssa Pirinelli and Nancy Carpenter, and my research advisor, Joe Alia, and of course, all my friends and my family. And I would love to take any more questions now.
All right, Connor.
Hi, nice job. I was just curious. You mentioned when you were showing the graphs for the different methods. There were, I mean, you had outliers for most of them. I was just curious if you noticed any trends in like which molecules were outliers. Like, oh, chloroform always was an outlier, or like, oh, if it has this sort of functional group, it tends to be an outlier, or anything like that.
Yeah, so we didn't really see any commonalities between functional groups. There were some that intersected, but I don't think there were, I think that, and I have to think back now, if I remember correctly, we had a tendency to have groups that had, compounds that had NO2 as a functional group were often outliers. So like nitrobenzene was, I think, an outlier for all of them, which was interesting. There was usually at least one of either Aldrin, dieldrin, or endrin was usually one, but not consistently one of those. So I'm not perfectly sure why. So there were some overlap, but they was not consistently like every single time, other than NO2 subgroups on compounds.
Interesting. Thank you.
Yeah.
So I can't put my hand up as host, but I'm actually curious what the identity is of the one that was negative. So
Yeah,
one-
that was another and I'm pulling from several months ago in my memory. I think that was another one of our nitro somethings. I'm fairly certain it was another one of the ones within the NO2 group.
Thank you. And I have another kind of connected question. What was your favorite part of doing this research?
I really enjoyed building molecules in Gaussian. I thought it was a lot of fun, with the exception of the Hexabromocyclododecane, because it was really a pain to try and get the stereochemistry right on all 6 bromines and then do it again on the next of the 3 stereoisomers.
Stereochemistry is the worst sometimes. All right, Cal.
First of all, amazing job. I guess sort of a follow-up question is, do you have any idea why these nitro groups are acting up on you? And any theories, hypotheses you want to throw out there?
No, because to be honest, until Connor just brought up that question, I hadn't even thought about the fact that the nitro groups were common across all of my outliers. Also, congrats on your summer program. Okay, Joe.
Nice work, Emily.
Thanks.
I just want to get back to the biological fat part, because there's more to be said there, I think. Which of the solvents that you modeled happens to be a biological fat?
Yeah, olive oil is a biological fat. It comes straight out of biology. Olives, well, those aren't biology, but comes straight out of a biological substance.
Okay, that's just my question. The reason why I bring it up is that if the compounds are being absorbed into animals, quite likely the substance that they're being absorbed into is more like olive oil than like octanol.
Yeah.
So,
Joe, is your hand still up? Hand is down. Okay. Any other questions for Emily? Jen?
So I will risk being somewhat revealing my age, but did you say that these seemed long whenever they took about 20 minutes?
They did. I know that that's that's nothing, but too long to me.
Right. The reason is I worked with Gaussian in graduate school, and it was not uncommon to be multiple days, and you had to hope that it didn't crash before then. So just sort of a little bit of perspective.
Yeah, no, Joe was telling me a little bit about that while we were working on it.
same comment.
All right, if there are no other questions for our speaker, I will remind students and faculty to please fill out the student faculty evaluations respectively. So other than that, let's give Emily a either clap if your video's on or the clappy happy emoji thing in the reactions button. Great, thank you everyone.
Nice job, Emily.
Great job. Good talk. Lots of great work. It was fun to see.
Thank you.
I thought you did a really good job.
Thanks.
Yeah. All right. I think if I disappear, you will be the host. So if you want to chat with the people who are still here, you are welcome to, but I'm going to disappear. So.
Okay.